Quantum information is known for being extremely fragile, while modern internet traffic carries enormous amounts of data through fiber optic networks every second. In a new breakthrough, scientists at Northwestern University demonstrated that both can successfully travel through the same fiber optic cable. The researchers transmitted entangled photons across a 24.4-kilometer or 15.2-mile fiber optic connection linking Evanston and downtown Chicago, while the same cable simultaneously carried high-capacity commercial internet traffic. Despite the heavy flow of conventional data, the quantum signals remained intact, preserving quantum entanglement with more than 94% fidelity. The study, published in Optica Quantum, marks the first demonstration of entanglement distribution between remote locations over an optical fiber that simultaneously carries modern commercial telecommunications traffic. According to senior author Prem Kumar, quantum signals are tiny compared with conventional communication signals, comparing the experiment to an ant traveling through a path filled with elephants.
Unlike today's internet, which stores information as binary bits, future quantum networks rely on quantum states known as qubits. One of their defining properties is quantum entanglement, in which two particles remain linked regardless of the distance separating them. Instead of physically carrying information, entangled particles can enable the exchange of quantum information through a process called quantum teleportation. Although this approach offers extremely fast and secure communication, it is also highly sensitive because even small amounts of optical noise can interfere with the single photons carrying quantum information. Prem Kumar explained that all optical communications use light. Conventional communication signals typically consist of millions of particles of light, while quantum communication depends on individual photons, making quantum signals much more vulnerable to disturbances. In a 2024 study, Kumar and his collaborators discovered a way to better protect quantum photons. After studying how light scatters inside fiber optic cables, they identified a quieter wavelength where the photons could travel with less interference. The team also introduced special filters to reduce noise generated by ordinary internet traffic. Laboratory experiments using a 30-kilometer, 19-mile fiber carrying high-speed internet traffic demonstrated that the approach was successful. Kumar described those experiments as proof that the concept could work in the laboratory, while the next objective was to test the technology under real-world conditions. For the new experiment, the researchers generated pairs of entangled photons at Northwestern University's Evanston campus. One photon from each pair remained in Evanston, while its entangled partner traveled 24.4 kilometers through installed fiber optic cables to the Starlight International National Communications Exchange facility on Northwestern's downtown Chicago campus. At the same time, the optical fiber carried two 800 gigabits per second classical data channels, along with additional optical power representing a fully loaded commercial telecommunications link. According to Kumar, the fiber contained enough optical power to potentially support 36 terabits per second of classical data transmission, roughly equivalent to 20 million YouTube videos streaming simultaneously through a single optical fiber. To protect the quantum photons, the researchers placed them in the quieter O band, while conventional communications remained in the C band, where commercial systems normally operate. Because the experiment connected two physically separate locations, both ends of the network had to remain synchronized with extraordinary precision. Using an optical timing system called White Rabbit, the team achieved synchronization accurate to within trillionths of a second. This precision allowed the researchers to identify matching pairs of entangled photons in real time, despite the heavy background traffic.
Measurements confirmed that the entangled photons maintained more than 94% fidelity, demonstrating that the quantum entanglement survived transmission at a level that cannot be reproduced by classical communication systems. The researchers explained that this work is part of a broader effort to integrate quantum technologies with existing telecommunications infrastructure. Their next objective is to perform quantum teleportation between remote locations across a real-world telecommunications network carrying commercial internet traffic. According to Kumar, the first step is distributing quantum entanglement, while the second is transferring quantum information itself. Although each step becomes progressively more difficult, the study demonstrates that both are becoming increasingly achievable.